Okay, we have a question. If this u comma v operation is equal to c1 u1 v1 plus c2 u2 v2, where u is still our vector u1 u2, v is our vector v1 v2, then the question is, does this operation have properties that are, I say the same, I'll put quotes around that, really analogous to the properties of the dot product, okay? If you have the, quote, same properties as a dot product, if this operation has the same properties as a dot product, we call it an inner product. Well, the first property we'll look at is, does the inner product of v and v give us something that's never negative? It's got to be greater than or equal to 0. And this is just like what we proved just, very recently, just a couple of clips earlier, that v dot v has to be greater than or equal to 0. If you're using a dot product, that is true. Okay, well, let's see what it takes for this this operation to give us always a number that's greater than or equal to 0. Now, we're not sure that this really does, but let's check it out and see if it does. Okay, so if we do this, which means this, then we've got to get C1 times U1 V1. C1 times this number, just U1 V1. If you got V1 V1, then you got to do those. Plus C2 U2 V2. C2 times this number. That would be C2 times this number times this number. That would give us C1 V1 squared, or V1 V1. And C2 times V2, which is C1 V1 squared plus C2 V2 squared. Well, we begin to see how this could always be greater than or equal to 0 because V1 squared and V2 squared are always greater than or equal to 0. However, there's a little bit of a fly in the ointment here. We've got to put some restrictions on things. We haven't said that C1 and C2 have to be greater than or equal to 0. So if one of these is negative, it might be that that's enough to, in some cases, make the inner product of v with v less than 0. And if so, then we're going to say this isn't an inner product. It doesn't have a property that's analogous to the property of the dot product, where the dot product is all of a vector with itself is always greater than or equal to 0. Okay, so, well, we test. Okay, is v dot v greater than or equal to 0? If C1 and C2 are both greater than or equal to 0, then we're sure of it because, both these numbers will be positive. You get a positive when you add them. Okay? Now, I digress to another question here. Then it was unnecessary to do that. So I'm going to say, so let's require that C1 is greater than or equal to 0 and C2 is greater than or equal to 0. And I'll just say that, well, if either one of these numbers is less than 0, say C1 is less than 0, then if V2 happens to be 0, which is perfectly legitimate, could happen for some vectors, it will happen for some vectors. If V2 is equal to 0, then you're going to have C1 V1 squared. If C1 is negative, that makes this negative, so there is a vector that gives you a negative when you do this. And when we say that V, the inner product of V with V has to be greater than or equal to 0, that means it's greater than or equal to 0 for all vectors V. Okay, if C1 was negative, then, for example, the vector V equal to 1, 0 would give you negative 1 times V1, V1, negative V squared. That would be 0. Okay, so we're going to require that C1 and C2 both be greater than 0. If we do, it's going to turn out that this is an inner product. Now, there are a bunch of properties that the dot product has, and we're not mentioning all of them. We're just looking at how we would deal with proving these sorts of properties. You have to verify all the properties to show that this is, in fact, a dot product, but I believe it is. Test that. I might be wrong. Okay. Another property is that the dot product or an inner product would have to be 0 if and only if the vector v was 0. Okay? And now, that's only going to be so if we require that both C1 and C2 be greater than 0. We can't let them be equal to 0. Okay, we could get this property if we let C1 and C2 be greater than or equal to 0, but we don't get this property unless they both happen to be greater than 0. So when I said this turns out to be an inner product, as a step ahead of myself with this property, but we'd only established this property, so I wasn't really right when I said that with this restriction. But with this restriction, this is so, and the other properties will also follow. And many of those properties work just fine if C1 and C2 could be negative, or one positive, one negative. There are properties of the inner product that we can verify that don't depend on C1 and C2 both being positive. However, this property does depend on both these numbers being positive.